Welcome to a new episode.
Hello and welcome back to the Copper Connection podcast, your go-to podcast for practical, real-world plumbing, electrical and BSc knowledge in construction. As always, I'm your host, Chris Bailey, and today we're unpacking how electricity is generated, transformed and distributed, what that means on site and in buildings, and the protective devices and safety principles that keep people and property safe. We'll also weave in the key UK regulations and standards you need to know so you can align practice along with compliance. Okay, let's sit back, let's plug in and get into this week's episode. So now we're going to look at how electricity is generated and why it matters. Electricity is generated generation rests upon a simple but profound principle. Move a conductor through a magnetic field and you will induce a voltage. Electromagnetism induction. That's the beating heart of generators and alternators. We have different types of fuels that we can use to generate electricity. We have fossil fuels, so coal, oil and gas are burned to produce heat, which turns water into steam to spin a turbine connected to a generator. We have nuclear power. In practice, the UK's civil nuclear plants use nuclear fission, not fusion, to create heat, again producing steam to drive turbines. And then we have our renewable energies. Wind turbines rotate directly in the wind. Hydroelectrical systems use the fall or flow of water, and solar PV convert light into DC electricity, with inverters to produce AC for the grid. Once generated, electricity is stepped up to very high voltage to travel efficiently across long distances, and then stepped down near to where it's going to be used. Understanding the upstream generation and transmission explains why we work with certain voltages, why three-phase power is common on large projects, and how safety and protection strategies are designed. So let's have a quick refresher on the key units. We have current in amps, which is A, the flow of the charge. Lighting circuits often have lower currents. Power circuits carry high currents. Voltage is in volts. B, electrical potential. It's the pressure that pushes the current. Then we have resistance in ohms, opposite to current. And power in watts, the rate of energy transfer. So the core relationships are P equals V times I and V equals I times R. Knowing these lets you size conductors, select protective devices and anticipate load and voltage drops. So now let's have a look at induction and transformers. Electromagnetic induction is the basis of transformers too. With AC, a changing magnetic field in a core link to two windings. First, we have step-up transformers that increase voltage and reduce current, ideal for minimizing losses over distance. Then we have step-down transformers, which decrease voltage and increase current, essential near loads. Three-phase versus single-phase. So single-phase is what most domestic properties received, which is 230 volts. Three-phase systems deliver high power density and smoother torque for motors, commonly at 400 volts, line to line, and 230 volts, line to neutral, in UK star-connected systems. On big jobs or industrial sites, three-phase is your friend. Efficient distribution, smaller conductors for the same power, and better motor performance. So now let's have a look at how we get power from the grid to site. In the UK, the national grid transmits electricity at very high voltages. Commonly, 275 kilovolts and 400 kilovolts. Why so high? Because power loses scale with current squared. Stepped up voltage reduces current and losses. Closer to end users, substations step down voltage to distribution levels, then to service voltage for buildings. Star Distribution in the UK provides both 230 volt single phase for domestic and small commercial loads and 400 volts three phase and neutral for commercial and industrial loads. Pylons, underground cables, ring mains and local substations all play a part in dependable delivery. Now we're going to take a look at AC versus DC and side voltages. DC is unidirectional and steady, used in likes of batteries, EV chargers and electronics like it. AC alternates, which makes transformers possible, hence its dominance in the grid and building power. On construction sites in the UK, 110 volt reduced voltage systems are standard for portable tools, often via 110 volts centre tap to earth, or CTE. Transformers that give 55 volts relative to earth. That dramatically lowers shock risk if a single conductor contacts a person or earth. So now let's take a look at some of the different protection devices: fuses, MCBs, RCDs and RCBOs. Protection devices are there to disconnect dangerous faults quickly. Fuses, a calibrated element, melts under excessive current. MCBs, miniature circuit breakers. Thermal and magnetic, so the overload and the short circuit trip elements. They are resettable and have characteristic curves B, C and D for different inrush behaviours. Then we have RCDs, which is a residual current device. Detects an imbalance between the live and neutral. Indicates a leakage to earth to trip rapidly. Typical ratings: 30 milliamps, additional protection against electric shocks for sockets and many final circuits. 100 milliamps or 300 milliamps, often for fire protection or upstream selectivity. We have RCBOs, combined overcurrent protection like an MCB and a residual current protection like an RCD, all in one device. These devices underpin automatic disconnection of supply, or ADS, when a fault occurs. Your protective device must disconnect within prescribed times to keep voltage and shock energy within safe limits. Okay, now let's take a look at earthing, the return earth path and earth loop impedance. A safe installation depends on a reliable earth fault path, so fault currents are high enough to trip the device within the required time. Earth loop impedance, or Z, the total impedance of the fault path from the source through the line to the fault point and back via the protective conductor and earthing system. Lower Zs generally mean faster disconnection. Measuring or calculating Zs ensures compliance with disconnection times. As a rule of thumb, in many TN systems, 0.4 seconds disconnection for final circuits at or below 32 amps supplying sockets, outlets or handheld equipment. 5 seconds for distribution circuits or higher rated circuits. Always verify the device time current characteristics with the applicable standard. Earthing arrangements, so TNS, TNCS, TT, affect your approach. TT systems often require RCDs because achievable earth loop currents may be too low for overcurrent device to trip quickly. Okay, so let's take a look at some key UK regulations and standards you must know. While designing choices and good engineering practice matter, compliance is non-negotiable. For power and distribution in the UK context, ensure you're aligned with the following. So we have BS 7671 2018. This is the IET wiring regulation, plus Amendment 2 that was issued in 2022. This defines requirements for design, selection, and erection protection, inspection, and testing of electrical installations. We're going to have a look at some chapter highlights that are relevant here. So we've got part 4 for protection for safety, especially chapter 41. Protection against electric shock. Chapter 43, protection against overcurrent. And chapter 44, overvoltage. Chapter 52, selection and erection of wiring system for cable routes, supports and environmental considerations, including requirements like metallic fixings for wiring systems in escape routes. We have Chapter 53, protection, installation, switching, control and monitoring, device selections and coordination. We have Part 7 for special locations where applicable, construction sites, Section 704, bathrooms 701, and outdoors. ADS RCD additional protection, for example, the 30 milliamps on many socket circuits, Z's limits, disconnection times, and device characteristic curves. Amendment 2 introduced, among other things, updates required around the AFDDs in certain circumstances. SPDs, considerations, and labelling documentation updates. Always consult the latest edition text for precise requirements that apply to the installation. We have the Electricity at Work Regulation 1989, a legal framework requiring electrical systems to be constructed, maintained, and used to prevent danger. This places duties on employers, employees, and the self-employed to ensure safety. The HSE Guidance HSR 25 provides the authoritative approved Code of Practices, ACOP, and a guidance on compliance with the regulations. We have building regulations in England and Wales Part P for electrical safety for dwellings, applies to the electrical installation in homes and certain related spaces. Requires that a reasonable, responsible person is made for the design, installation, and electrical installation to project persons operating, maintaining, or altering them. Many domestic workers are notified and must be certified by a competent person or inspected by building control. We have the electrical safety, quality, and continuing regulations. This governs public distribution, networks, and interfaces with consumers' installations. This is particularly relevant at the point of supply and earthing arrangements provided by the distributor. We have the CDM Regulations 2015, which is a construction design and management regulation. This sets out the roles and responsibilities for clients, designers, and contractors to manage health and safety risks in construction. Electrical risk and temporary work planning, including 110-volt systems and site distribution, fall within the CDM risk management. Product and equipment standards, so BS-EN 61439, full low voltage switchgear and control gear assemblies, distribution boards and panels. We have BS-EN 61008, 61009, 898, 60947 is a series for RCDs, RCBOs, MCBs, and circuit breakers. BS-EN 6024 for machinery, electrical equipment, where relevant. Guidance on good practice, the IET on-site guide and guidance notes, for example, GN1 section and erection, GN3 for inspection and testing, to interpret BS 7671 particularly. HSE guidance for commercial construction, electrical safety and temporary electrics on site. Please note, and this is super important, that always check the latest editions and any local amendments. If you're in Scotland or Northern Ireland, equivalent regulations and approval systems apply with your local nuances. Okay, so now we're going to take away some practical construction takeaways. Choose the right system voltage. On site, use 110 volts CTE for portable tools via compliant site transformers. This significantly reduces the shock risk. Plan three-phase distributions early. For commercial industrial projects, three-phase 400 volts with appropriate diversity, load, balancing and motor starting needs avoid costly rework. Size conductors and protections together. Use P equals VI and devise curves. Verify Z to meet disconnection times. Calculate or measure perspective fault currents. Coordination protection. Selecting tripping prevents a minor fault from blacking out the whole project. Consider time-delayed RCDs upstream and RCBOs downstream. RCDs where required and where 30 milliamps for additional protection on many final circuits, especially socket outlets and outdoor circuits. Use appropriate types AC, A, F and B based on load characteristics like EV chargers, VFDs or PV inverters. Earthing matters. TNCS versus TNS versus TT will change how you meet ADS. In TT, expect RCD resilient and careful electrode design and testing. Temporary works under CDM. Keep temporary distribution tidy, protected mechanically, labelled, routinely inspected and tested. And always make sure it's documented. Test and certify. Inspection, testing and documentation are optional. Record the Zs, R+, R1 plus R2, installation resistance, RCD trip times and prospective fault currents are required by British Standard 7671 and your QA processes. So just a little myth check. A quick correction you'll sometimes hear. Civil nuclear power stations today use nuclear fission, not fusion. Fusion remains developmental. The rest of the process, heat, steam, turbines, generators, lines up with other thermal plants. So let's recap what we've covered so far in this episode. Generation uses electromagnetic induction. Distribution steps voltage up and down to manage losses and usability. Three-phase 400 volts and single-phase 330 volts are the UK norms from a star system. On construction sites, 110 volts improves safety for portable tools. Protection devices, fuses, MCBs, RCDs, RCBOs exist to meet ADS and keep people safe. Earthing and earthing loop impedance are critical to ensure disconnections within required times. We need to stay compliant with all the British standards and the CDM 2015 and Part B regulations. And relevant British standards, product standards. Okay, so that's a wrap for episode 8 of the Copper Connection podcast, where we have looked at power and distribution. If this helped clarify the bigger picture from grid to socket, from theory to safe practice, share it with a teammate or apprentice. In our next episode, we will continue through construction as a whole, pick a topic and apply these protectives during installation and testing.
We'll be back next week. In the meantime, please subscribe and thanks for listening.